Hello there and welcome back to the Sleep Science. Outside your window, the street is still. Somewhere in Montana, snow is collecting on an empty road. In Miami, the moon is polishing the tops of swaying palms. And over all of it, unseen and mostly unbothered, the sky is humming. Above your head, about 300 miles up, something is happening. You can't see it, but Earth's magnetic field is straining like a ship's sail in a sudden gust. Tiny particles born in the sun's upper atmosphere and flung across space at 1,000,000 miles per hour are slamming into our upper atmosphere. And here you are, under blankets and blinking slowly, completely unaware. You probably won't survive this. Well, not this exactly, but one of these days the sun may decide to reach just a little too far. Maybe you'll wake up and your GPS is blank, your lights don't work, and your neighbor is using a ham radio like it's 1942. Don't panic yet. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, where are you listening from? Drop your location and the local time in the comments. I love seeing how global our sleepy crew really is. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The humming is real, not audible, unless you've somehow developed ears that can hear magnetic field vibrations, but real nonetheless. What you're picking up on, maybe without even realizing it, is space weather. The phrase sounds made up like gravity mood or cosmic vibes, but it's a real branch of science. And right now it's having a moment. See, while the U.S. sleeps, while you roll over in your flannel sheets and your phone buzzes softly with updates from a world you're not even dreaming of, the sun is still very much awake. And tonight, it's doing something unusual. Solar wind, that ever-present breeze of charged particles, has gotten a little punchier. It's been surging lately. NASA's data says the solar wind speed has been climbing past 600 kilometers per second, and the Earth's magnetosphere, the invisible force field that wraps around our planet, is responding like a drumhead under sudden stress. Imagine the entire planet enveloped in a shimmering, teardrop-shaped shell of magnetism. It stretches farther on the night side than the day side, pushed like a tail by the relentless solar wind. And tonight, that wind is tugging at our tail, stirring up what scientists call a geomagnetic storm. So this isn't just poetic, it's a classification. Think mild, moderate, strong, kind of like how you order salsa, only it determines whether your airline reroutes over Canada. When these storms happen, you sometimes get auroras, pretty ones. That's the polite surface-level reaction, like Earth saying, "Oh, you're angry? Let me wear something sparkly." But that glow, it's a battlefield. It's caused by energetic particles, protons and electrons, that slam into Earth's upper atmosphere and collide with oxygen and nitrogen atoms, releasing bursts of light in greens, purples, and rare reds. A luminous bruise across the sky. In fact, right now, if you could step outside and if you live far enough north, you might see faint curtains of color pulsing above you. That's the visible part. But there's also the invisible part, the induced currents slithering through power lines, the interference in satellite signals, the strange disruptions in radio traffic, all while you sleep. There was a time when people thought auroras were dragons, flaming sky serpents. The Chinese word for aurora translates to red vapors. The Inuit called them the spirits of the dead, dancing. You may not see any dragons, but if you've got one of those aurora tracking apps, and I know some of you do, it probably pinged an alert about elevated geomagnetic activity tonight. That's why we're here. The sun has entered an active phase of its 11-year cycle, and with that comes unpredictability, flares, coronal mass ejections, and odd little burps of radiation that ripple through space like a cosmic hiccup. The most recent event? A surprise G2 class geomagnetic storm last week, unexpected, abrupt, and perfectly timed for those watching from Europe and the Arctic Circle. America mostly slept through it. You wonder for a second what's happening right now over Siberia or Finland. Maybe a family's outside, cheeks red with cold, gazing up in silence as light dances over them. Or maybe someone's running late for work, unaware their location tracking GPS is just slightly off, pinging between imagined towers, all thanks to the sun's invisible tantrum. Historians still argue whether these storms have always been this intense or if our increasing reliance on electronics just makes us more sensitive. One camp says, same storms, more fragile tech. Another argues the sun's activity has evolved across centuries. After all, we've only been measuring it with precision since the 1600s. And even then, Galileo nearly blinded himself doing it. Casual, but tonight is measurable. Satellites are blinking. Ground stations are recording tiny voltage shifts. Magnetometers, devices that measure fluctuations in magnetic fields, are jittering like caffeine addicts. Somewhere in a bunker, a scientist is probably nudging their glasses up and saying, that's interesting, which in scientist speak is code for mild panic. And you're here, under your blankets, listening. Still for now. The humming continues, not in your ears, but in the thin shell of charged particles high above. It sounds like quiet if quiet had a heartbeat, pulsing, pressing, unseen but not unfelt. You might dream of it later. Sky serpents slithering through the ionosphere, or invisible fingers playing with the earth like a harp string. Maybe you'll wake up and the power will be out. Or maybe the fridge will hum along like nothing ever happened. And you'll never know that while you slept, the sun flung 1 billion tons of plasma toward your planet, and Earth caught it like a pro. No big deal. It only happens all the time. You, a planet, and 93 million miles. You are, without quite realizing it, in a long-distance relationship with the sun. It's not one of those polite pen-pal sorts of arrangements either. This is a high-intensity, 93 million mile tether made of light, magnetism, and a daily flood of radiation. You don't really get a say in the matter. Every breath you take, every surface you touch, and every text message bouncing from your phone, all of it is built on the sun's very generous, very unstable gift of energy. Right now, as you're drifting off, that energy is traveling through space. It left the sun's surface about 8 minutes ago, traveling at the speed of light. The photons, actual particles of sunlight, are slipping through your window, across your pillow, brushing your eyelids, even if they're shut tight. It's a soft kiss from a thermonuclear monster that burns at over 5,500 degrees Celsius. Cute, right? Of course, that's just the light. The real drama comes from the less punctual guests: solar wind, flares, and the occasional coronal mass ejection. These don't arrive in 8 minutes. They take their time, sometimes 2 to 4 days, depending on how fast and furious the sun decides to be. And right now, the solar wind has picked up speed. It's moving at over 700 kilometers per second, dragging high-energy particles and magnetic knots along for the ride. Here's the kicker. Earth has no choice but to accept the delivery. There's no return to sender for space weather. Our only real defense is a soft bubble of magnetism and atmosphere. A shield, yes, but one that can be dented. You're inside that bubble now. Safe-ish. Scientists call it the Magnetosphere, and it stretches out into space like a comet's tail. It protects you from being fried by cosmic radiation, scrambled by solar particles, or cooked by UV light. But it's not perfect. Some things get through, especially when the sun gets testy. And it's been testy lately. If you're wondering how all this invisible energy actually touches you, let's zoom in. Here, picture a solar flare, a sudden burst of radiation and magnetic energy, detonating near the sun's surface. It can release as much energy as 1 billion hydrogen bombs. The flare may be accompanied by a coronal mass ejection, CME, which is a fancy way of saying the sun just hurled a giant blob of plasma at Earth. This plasma cloud carries its own magnetic field, which can crash into ours and cause it to wobble, compress, or even temporarily flip direction. Like trying to pet a cat against the grain, it's not going to end well. When that happens, things get weird. Satellites in low Earth orbit start to feel drag from the swelling upper atmosphere. GPS signals become unreliable. High-frequency radio can cut out, especially near the poles. In extreme cases, these interactions can even generate electric currents in the ground, currents that can overload transformers and cause regional blackouts. If you're lying in bed with your phone charging beside you, Think of all the satellites and transmission lines currently being watched closely by space weather teams. Not because they will fail, but because, under the wrong kind of solar pressure, they very well could. Historians still argue whether these solar interactions have influenced major events. Some fringe researchers point to anecdotal data linking geomagnetic storms to human behavior, spikes in aggression, sleep disturbances, even stock market volatility. Is it pseudoscience? Maybe. But the human brain does run on tiny electrical impulses, and geomagnetic storms do, undeniably, rattle the ionosphere, distort radio signals, and induce electric currents deep in the earth. Could they tweak your brain chemistry just a little? The science is unsettled, but it's a deliciously spooky thought. You probably didn't think about this today while brushing your teeth or waiting for the microwave to finish reheating leftovers. But every electronic thing you touch today owes its life to a sun that's 93 million miles away, and that occasionally throws fits big enough to crash the entire planetary system of convenience you've grown up inside. And that tether, the invisible string tying Earth to its star, it pulses constantly. Solar physicists track it through something called the Parker spiral. It's the shape the sun's magnetic field takes as it spirals outward through the solar system, warped by the sun's rotation. Think of it like an invisible sprinkler, spinning out charged particles and magnetism in a slowly twisting corkscrew that Earth plows through on its orbit. You are, at this very moment, moving through one of these spirals. Earth is cruising through a current sheet, a folded ripple in solar magnetic fields. The solar wind is streaming across this boundary, loaded with more energy than usual, like wind through a canyon. That's why tonight's storm is special. It's not the biggest we've seen, not yet, but it's one of the strangest in recent years. The sunspot that triggered it wasn't supposed to be very active. It wasn't even visible on the sun's Earth-facing side a week ago. It just rotated into view and let loose, like an old furnace coughing smoke after years of quiet. Sunspot AR 3529, yes. They named them like serial killers, erupted with an M-class flare, and tossed a CME directly at Earth. It wasn't the most powerful type, those would be X-class flares, but its direction and timing were unusually direct, and that means ripple effects, swirling ionospheric eddies, weakening signals, power grids flickering, a shimmering aurora brushing down into states that don't usually see them. Maybe even your state. So, you roll over, you check the window, still darkness. But up there, far above your roof in the sleepy clouds, a storm is pressing on Earth's skin like a slow, glowing fingerprint. It won't break the planet. It's not that kind of drama, but it will be remembered, logged, studied, and maybe, just maybe dreamed of by someone like you, drifting off while the universe plays a quiet symphony of magnetism overhead. Your blanket of magnetism. You sleep under layers, fabrics, comforters, maybe a weighted blanket if you're fancy, but your real blanket is vast, invisible, and always on. It stretches tens of thousands of kilometers into space, rippling gently under the solar wind's breath. You are, quite literally, tucked in by Earth's magnetic field. This field isn't a perfect bubble. It's a warped, living structure that sways and pulses like a jellyfish, drifting through solar currents. It's called the Magnetosphere, and it protects you from the sun in ways you probably never thought to appreciate, unless you're one of the rare few who daydream about charged particles and planetary shielding. In which case, welcome. You're among friends. The magnetosphere is created by Earth's molten iron core, which churns and flows like a slow, subterranean lava lamp. And that motion generates electric currents, which in turn produce magnetic fields. It's called the geodynamo, and it's the reason your compass doesn't spin uselessly in every direction. Though to be fair, it does wobble every now and then. That's a different story. We'll get to that. Tonight, this magnetic blanket is under pressure. As the solar wind strikes the Earth, the magnetosphere compresses on the side facing the sun and stretches out behind us into a long tail. Like a windsock at an airport during a storm. That tail extends well past the orbit of the moon. You didn't know Earth had a tail, did you? It's always there, silently flailing behind you in the solar breeze. Now, when a particularly fast or dense wave of solar particles hits, this protective structure ripples. Imagine someone thwacking a trampoline with a leaf blower. And when the magnetic lines of force, normally smooth and taut, start to twist, reconnect, and snap. This process is known as magnetic reconnection, and it can release more energy than all the power plants on Earth combined. It's also what triggers those shimmering auroras we keep talking about. But more on that soon. Tonight, the magnetosphere is dancing, swaying and trembling with solar rhythm. Satellites in geostationary orbit, about 22,000 miles above the equator, are moving through a space that's anything but calm. Their electronics are hardened against this kind of thing, but even the toughest systems can be tricked by a well-placed proton. That's why agencies like NOAA and NASA keep 24/7 eyes on what's happening up there. There are people whose entire jobs are just watching the magnetic field breathe. And breathe it does. You probably imagine the magnetosphere as a smooth field of lines arching from the North Pole to the South, like a textbook diagram. But in reality, it's more like a tangled slinky being yanked around in a wind tunnel. Flux ropes, plasma bubbles, and electric currents swirl within it. These are the kind of phenomena that give supercomputers migraines. One fringe theory, lovingly called space tornadoes, suggests that spiraling, cyclonic flows of plasma can form within the magnetosphere, transferring energy from the solar wind deep into Earth's atmosphere. We're talking thousands of kilometers wide, spinning at thousands of miles per hour. Imagine an aurora-powered blender and you're halfway there. Historians still argue whether ancient civilizations ever felt these storms before they had words for them. Some scholars believe unusual animal behavior, tribal myths of sky snakes, or even ancient power outages, red, fire refusal to light, could be linked to historic magnetic events. One Japanese record from the 7th century describes a night when the heavens turned to fire, long before auroras were understood. You don't see the magnetosphere, but your body feels its stability. Birds use it to migrate. Whales may use it to navigate across vast oceans. And you, without knowing it, rely on its protective cushion every single day, especially if you fly, use electricity, or, say, exist without being irradiated into oblivion. When that shield weakens or is stressed, like tonight, space weather comes closer to home. Right now, Earth's magnetic field is jittering. Sensitive instruments across the globe are registering spikes, K indexes climbing above average. That's a measure of geomagnetic activity. KP levels of 5 or higher mean minor storms. Hit 7 or 8, and now you're talking potential blackouts in high-latitude grids. Hit 9? That's the kind of thing that turns power station operators into night owls. Your power's still on, thankfully. But tonight's disturbances might be enough to cause low Earth orbit satellites to slow just a bit as the atmosphere swells, or to make GPS mapping just inaccurate enough to turn a self-driving car into a hedge trimmer. Don't worry, it's all monitored. Mostly. But here's something charming. In the far northern and southern latitudes, pilots flying polar routes will already be adjusting. Their radios crackle strangely during geomagnetic storms. Some airlines reroute flights entirely to avoid the pole's magnetic chaos. Those who do fly through it are trained to use backup systems and keep radiation exposure logs, especially during solar maximums. You just snuggle deeper into your covers. There's something oddly comforting about it all, isn't there? That even as the sun flings charged particles across space and Earth's magnetic field undulates in defense, you can still lie here, completely fine. It's easy to forget we live on a rock suspended in space, being actively protected by a planetary force field. But that's exactly what's happening, right now. And the magnetosphere isn't a passive thing, it fights back. When the solar wind is strong, the field strengthens in some places and stretches in others, forming pockets of trapped particles. And these are the Van Allen belts, donut-shaped radiation zones girdling the planet like invisible energy hula hoops. And yes, astronauts try to avoid them. Your brain might be wondering if all this magnetic fluctuation affects your sleep. And weirdly, there's some debate there. One fringe corner of sleep research has found possible correlations between geomagnetic storms and sleep disturbances, even vivid dreams. Some small studies hint at a link between solar activity and human melatonin production. Is it science? Kinda. Is it settled? Not even close. Still, if you feel a little buzz tonight, a sense of restless energy or a strange clarity, it might not be all in your head. It might be Earth's magnetosphere, breathing faster under pressure, and you, like a feather in its current, just drifting through the charge. Sunspots, cosmic freckles of mayhem. If you looked up at the sun right now, don't, but if, you'd see what looks like a flawless, golden white sphere glowing with perfect, unbothered serenity. Except it's not. Zoom in a little, closer. No, even closer. Use a special telescope, one with filters so you don't melt your eyeballs. Now you'll start to see them. Dark little blotches peppering the surface. Some small, others big enough to swallow Earth whole. These are sunspots, and they are not just celestial acne. They are the outward signs of inward turmoil, magnetic chaos bubbles, regions of ferocious energy twisted into temporary stillness. They look calm, but you should know better by now. Each sunspot is cooler than the area around it, which is why it appears darker. While the sun's average surface temp is around 5,500 degrees Celsius, sunspots hover closer to 3,500. That's still, insanely hot, but it's all relative when you're made of nuclear fire. And here's the twist. Sunspots are the least of your worries. The real danger is what they often precede. Remember that sunspot from earlier, AR3529? That innocent-looking speck on the solar surface? It's a tangle of magnetic fields so tight, it's like someone twisted a ball of rubber bands until it snapped. When that magnetic tension releases, you get solar flares, those brilliant flashes of X-rays and ultraviolet light, and sometimes, if the sun is really feeling dramatic, a coronal mass ejection too. Think of a sunspot like the seething eye of a hurricane, or the pin pulled on a grenade. Historians still argue whether sunspots were ever visible to the naked eye in ancient times. Some records from China suggest people saw black dots crossing the sun, especially during sunrise or sunset when the light was dim enough. One 12th century Korean account describes a dark guest star moving across the sun for 3 mornings. Sounds poetic, also terrifying. Galileo was among the first Europeans to document sunspots with telescopes, which was bold considering he was already in trouble for implying Earth wasn't the center of the universe. He even drew them, these little scabs on the sun's surface, and watched them move, grow, and disappear over days. It was the 1600s equivalent of solar live streaming. Now you've got whole space missions, like NASA's Solar Dynamics Observatory, staring at the sun 24/7 in more wavelengths than your eyes can even comprehend. And what they're seeing lately? It's a bit spicy. Watch, the current sunspot count is higher than it's been in years. Solar cycle 25, the one we're in right now, was expected to be mild. That prediction? Not aging well. The number of active regions is climbing, and the sun seems to be firing off flares and burps of plasma like a toddler hopped up on Mountain Dew. Each sunspot is named and tracked, just like a tropical storm. We've already had several M-class flares this month, and an X-class is always looming in the wings. You might not hear about them unless they cause real drama, like knocking out a communications satellite or creating an aurora over Georgia. But they're happening, whether or not your group chat mentions it. Tonight, the sun is rotating, slowly, methodically. It takes about 27 Earth days to complete one full spin. As it turns, new sunspots are rotated into view, while others vanish around the back. AR3529 is just one of many, and it's not alone. There's a whole family of magnetic misfits coming into frame. And yes, Earth watches them with the kind of intense focus usually reserved for dating apps and playoff brackets. Because when a sunspot is Earth-facing, meaning its burps and flares are pointed directly at us, we get the full brunt of whatever it decides to do. Think of it like standing in front of a sneeze you can't dodge. Most of the time, it's just a cosmic spray, but every so often, it's a full lungful of disaster. Case in point, the Halloween storms of 2003. A cluster of sunspots erupted repeatedly, unleashing some of the most powerful flares recorded in modern history. Airlines rerouted, satellites failed, and astronauts aboard the International Space Station had to retreat to the most shielded parts of their orbital home. Trick or treat indeed. Tonight's sunspots aren't quite that dramatic yet, but they're active, unpredictable, and growing. You can actually see this in real time if you're the type to check space weather dashboards at 3 a.m. Don't lie, some of you are. Each dark patch, each twist in the solar fabric is a little pressure point, and you're 93 million miles away, hoping that when it snaps, it points somewhere else. Fringe Science Corner. Some researchers believe that sunspot activity could influence not just magnetic storms, but human culture. Patterns in ancient harvests, cycles of war, even stock market volatility have all been loosely correlated with solar activity. No, it's not astrology. But it's also not fascinating. Solar cycles have long tails, and the idea that the sun's temperament might ripple through human systems isn't completely off the table. You, though, just lie here. Maybe the thought of sunspots crawling across the sun like ants on a stovetop is oddly soothing. Maybe it reminds you how small your own problems are. That bill you forgot to pay? That awkward thing you said in the meeting? Pretty minor compared to a billion-ton plasma cannon warming up on the solar limb. As you exhale and settle into the stillness, remember, the sun isn't just shining, it's seething, rotating, shifting its magnetic skeleton, plotting its next eruption like an artist considering their next brushstroke, except the canvas is interplanetary space and the paint is fire. It'll be fine, probably. It's the Carrington wake-up call. You don't remember it, obviously, but the most violent solar storm in recorded history happened in 1859. And if that exact storm struck Earth again today, you wouldn't be listening to this right now. You'd be in the dark, literally. No Wi-Fi, no power, no lights, no fridge humming softly in the background. Just the quiet flicker of candlelight, a sky full of color, and a creeping sense that something has gone terribly, terribly wrong. They call it the Carrington event, named after British astronomer Richard Carrington, who on a perfectly ordinary September morning pointed his telescope at the sun and accidentally became the first human to witness a solar flare. He wasn't trying to change history, he was just sketching sunspots. But then, a blinding white flash exploded in his view. Carrington dropped his pen. Within hours, telegraph systems across Europe and North America began to fail. Sparks flew from wires. Operators were shocked, literally. Telegraph paper burst into flame. One system kept running even after it was unplugged, powered purely by the electromagnetic mayhem in the air. You've heard of wireless charging? This was wireless arson. It was the 19th century version of a planetary jump scare. You probably think of Victorian times as quaint and analog, and in many ways they were. But the telegraph was the first real-time global communications network, and it crumpled under the invisible pressure of a solar tantrum. That should concern you, considering how much more electric and networked your life has become since then. Historians still argue whether the Carrington event was a once-in-a-millennium storm or just one of many that happened to hit us dead on. Tree ring records and Antarctic ice cores show evidence of other massive events in 774 AD and again in 993. We'll get to those soon. But Carrington's was the first humanity watched unfold, and the only one we've directly measured with instruments. And you know what's really fun? We didn't even get the worst of it. The flare Carrington saw, bright enough to leave a temporary blind spot in his vision, was just the beginning. Roughly 17 hours later, a coronal mass ejection slammed into Earth's magnetosphere. That's record-breaking speed. Usually CMEs take 2 to 4 days to get here. This one was hauling, and when it hit, the auroras lit up the sky all the way down to the Caribbean. People in Cuba thought there was a fire in the northern hills. In Colorado, gold miners were woken by the glow and started making breakfast, thinking it was dawn. Telegraph lines stretched for hundreds of miles, lit up like Christmas tinsel, except slightly more on fire. Tonight, as you lie here under a mostly stable magnetosphere, know that events like Carrington's are still possible. Not likely, no, but not impossible either. Modern modeling suggests a storm of that magnitude today could cause $1 to $2 trillion in damage in the first year alone. Repairs would take months, possibly years. GPS satellites would be fried. Communication? Patchy at best. The power grid? Spotty, especially in higher latitudes. Fringe fact for the night, Some preppers call this scenario the sun kill shot. Dramatic, yes, but not entirely inaccurate. The U.S. The military has contingency plans. Utility companies run simulations. And somewhere deep in Colorado, there's almost certainly a guy in a hardened concrete room watching the sun through a wall of screens, just waiting to say, uh-oh. The last near miss? July 23rd, 2012. A powerful CME erupted from the sun, roughly Carrington class, and narrowly missed Earth's orbital path by about 9 days. If Earth had been just slightly ahead in its orbit, you wouldn't have heard about it in a sleepy YouTube video. You would have felt it. And here's something that might help or make you paranoid. We didn't realize how close a call it was until a year later, when researchers were reviewing satellite data from NASA's Stereo mission. So yeah, if something had hit, you'd have had about 12 hours warning, maybe less. But don't worry, when the satellites watching the sun are better now. The early warning systems are faster. And besides, what are you going to do? Run outside and block a CME with your hands? You're better off where you are, resting, listening, letting the distant roar of ancient firestorms lull you into a nice state of existential unease. Because here's the truth. The Carrington event wasn't unique. The sun does this kind of thing. It always has. It always will. We just happen to be living in a technological window fragile enough to care. In 1859, the world shrugged it off. Telegraph systems got repaired. Carrington's notes went into dusty journals. No big deal. But now, if a storm like that were to hit, you'd need to explain to your dog why the fridge doesn't open, why the lights won't turn on, and why their automatic feeders suddenly went rogue. And yes, you'd still have auroras. Beautiful, intense, blood-red auroras. Not just in Canada or Norway, but in Texas, in Rome, in Delhi. Skies lit up like something out of a fever dream. You'd want to take a photo, but your phone probably wouldn't work. You'd want to post about it, but the internet would be quiet. Not dead exactly, just sleeping. Like you. So you turn your head, shift your weight, feel the soft whisper of fabric against your cheek. Maybe you think of Carrington sketching by candlelight, or the telegraph sparks flying in the dark, or the strange apocalyptic beauty of a sky on fire before dawn. The sun isn't angry, it's just doing what it does, burning, burping, blasting. And Earth, ever patient, just braces for impact. The day satellites got amnesia. You wake up in March 1989, well, not you exactly, Hanar, but a lot of very confused Canadians. It's just before dawn in Quebec, and the lights have gone out. All of them. The entire Hydro-Quebec electrical grid has collapsed in less than 90 seconds. Power stations shut down, transmission lines fry, and for 9 hours, 6 million people live in an eerie quiet. No electricity, no heating, no traffic signals. Just the low hum of confusion and a lot of apologetic French. And above them, the sky is shimmering. This is what happens when space weather gets personal. You're probably thinking, why did a solar storm hit Canada? Why not somewhere with, say, fewer moose and better infrastructure? Well, it turns out being in a high-latitude region, closer to the magnetic poles, puts you right in the crosshairs when geomagnetic storms hit. The auroras might be pretty, but the invisible chaos beneath them is electric. Literally. These storms induce massive currents in Earth's crust, which then travel into power lines and transformers, especially in areas with long transmission paths and, shall we say, ambitious grids. On March 13th, 1989, the sun had been fidgeting for days. A series of flares and coronal mass ejections had been bubbling up from a particularly rowdy sunspot group. And then, bam, an X-15 class flare erupted. Just a day later, the CME arrived, and Quebec's grid folded like a cheap card table in a hurricane. But Quebec wasn't the only one feeling it. Satellites above the Earth began to misbehave. One by one, they started forgetting things, like where they were. Some drifted out of their orbits ever so slightly. Others experienced what engineers call single event upsets, where charged particles flip bits in the onboard memory. Think cosmic radiation playing roulette with your laptop's RAM. Only your laptop isn't floating in space at 17,000 miles per hour. That's when people started calling it satellite amnesia. One of NASA's tracking satellites stopped responding to commands for hours. A U.S. Navy navigation satellite began sending nonsense coordinates, and a GOES weather satellite, the kind that helps you know whether it's safe to grill tomorrow, momentarily forgot which way it was facing. Even the Space Shuttle Discovery, which was in orbit at the time, reported odd electrical glitches. Nothing catastrophic, just unsettling, like the ship itself was holding its breath. And all of this, from a star having what amounts to a magnetic mood swing. You don't think about it, but satellites are delicate creatures. They're engineered to survive the vacuum of space, wild temperature swings, and the occasional micrometeoroid. But geomagnetic storms are trickier. They can cause charging on the spacecraft's surface. This buildup of electric potential can suddenly discharge, frying circuits or interrupting onboard software. Imagine trying to do algebra while someone occasionally zaps you with static shocks. That's what being a satellite during a solar storm feels like. Historians still argue whether 1989 was a wake-up call or just the first in a long list of ignored warnings. Because even after all those fried transformers and grumpy geosynchronous satellites, it took another 2 decades for the term space weather to enter policy documents in any serious way. These days, we have better shielding, more sophisticated anomaly detection. Satellites carry redundant systems, and ground controllers have checklists a mile long for geomagnetic disturbances. But still, every storm is a gamble. Back on Earth, the Quebec blackout wasn't just a power outage. It was a moment of eerie vulnerability. Banking systems froze. Radio stations went silent. Even the backup power at a local airport flickered. One power company employee described it as watching a domino fall, then the rest falling in slow motion. You wonder maybe what would happen if it occurred today. Phones would die. ATMs would go dark. Air traffic control would scramble. Hospitals would fire up backup generators and pray. And you'd probably be sitting on your porch, blinking at the sky, and wondering why your smartwatch thinks you're hiking in Greenland. Oh, and you'd be watching one hell of a light show. Auroras were seen as far south as Texas that week, bright red arcs pulsing across the night sky. People called the police. Some thought it was a nuclear event. Others pulled their kids outside and told them it was angels dancing. A few just stared, silent, with their mouths open. Some things haven't changed. The auroras are still awe-inducing, still confusing to people who've never seen them, and they're still one of the few signs that the Earth is under magnetic siege. Fringe trivia for your sleepy brain. There's a theory that birds, especially migratory species, get temporarily confused by intense geomagnetic storms. They may even crash or detour en masse. A few ornithologists argue that bird migration patterns shift subtly after large solar events. Can't prove it yet, but it's a strange idea. Birds forgetting where to go because satellites forgot where they were. Space, it turns out, has a sense of humor. You lie there half dreaming and think about that moment in 1989, the moment when millions of people blinked in confusion, when the power vanished, when satellites stuttered, and when the sky glowed like an open wound. It passed, of course. Quebec's grid came back. Engineers repaired the transformers. The satellites were reset and recalibrated. But the echo of it still lingers in science labs and energy sector boardrooms. It's studied, modeled, feared. You wonder how close we came to a longer blackout, a bigger collapse. One nudge further, and maybe the storm would have cascaded into a continental outage. Or maybe not. Maybe the sun held back. Just a little. And tonight, it stirs again. Another sunspot brews. Another flare flickers. Somewhere, a satellite runs a diagnostic. Somewhere else, a grid operator sips coffee and watches the magnetometer twitch. And you, warm in your bed, drift deeper into a night stitched together by electric tension and starfire. Just don't forget your password in the morning. Would be embarrassing if the satellites weren't the only ones with amnesia. Tiny particles, big chaos. You're lying there, still, slow, relaxed, while above your head, billions of high-energy particles are colliding with the upper atmosphere in a silent, invisible war. Not to be dramatic, but it's kind of amazing your skull hasn't been turned into a glowing paper lantern. Okay, she may be a little dramatic, because the truth is, your planet's upper atmosphere is very good at its job, and its job primarily is to absorb the incoming hailstorm of radiation from space. Particles so small you'll never see them, and so energetic they could knock the electrons off atoms like a cosmic slap. These are not your garden variety molecules. We're talking about solar protons, electrons, and heavier ions, launched from the sun at near relativistic speeds. Every second, about 10 billion of these tiny bullets strike every square meter of Earth's atmosphere. And every time the sun throws a fit, say with a coronal mass ejection or a particularly spicy flare, that number spikes. So what happens to them? They smash into atoms in the thermosphere and ionosphere, stripping electrons and turning the upper layers of the sky into a writhing, glowing soup of plasma. That's the ionosphere's real personality, a layer of Earth's atmosphere, about 50 to 600 miles up, that becomes electrically charged when the sun is active. It expands, it brightens, and sometimes it gets rowdy. This is where things get weird. Because when this region of the atmosphere becomes unstable, it starts messing with anything that depends on bouncing radio waves or GPS signals off a stable sky. That includes satellites, planes, ships, and yes, your phone. Or more specifically, your phone's ability to know where the heck it is. Historians still argue whether early long-distance radio operators realized they were surfing solar storms. In the 1920s and 30s, hams and military communicators noticed strange dead zones, sudden bursts of static, or entire frequency bands going silent. Yet they had no idea the sun was having a full-blown outburst 93 million miles away. They just knew that sometimes the air itself felt wrong. Now we know better, mostly. Take, for example, the phenomenon of sudden ionospheric disturbance. The name is exactly what it sounds like. An abrupt, short-lived distortion in Earth's ionosphere triggered by solar flares. When a strong burst of X-ray radiation hits the upper atmosphere, the ionosphere's lower layers become over-ionized. That sounds like a party, but for radio operators, it's more like someone slamming a metal shutter over every frequency under 30 megahertz. High-frequency communication? Gone. Ships at sea? Deaf. Submarine communication? Useless. And it can happen in less than 10 minutes after a flare. But it's not just the ionosphere throwing shade. The particles themselves, those tiny, hypercharged interplanetary wanderers, can physically damage electronics. When they penetrate a satellite's casing, they can cause bit flips, sensor malfunctions, or even knock entire systems offline. One particle, one glitch, one big problem. There's even a specific term for this: single event effects. It's when a solitary cosmic ray disrupts the function of a microelectronic device. Not in a dramatic explosion, mind you. Just a silent, microscopic betrayal. It happens more than you think. Some satellites and even commercial airliners include software to detect and correct these flips. Others, they hope for the best. Fringe fact of the night: in 2003, a voting machine in Schaerbeek, Belgium, added 4,096 extra votes to a candidate's tally during an election. Upon investigation, my scientists concluded the likeliest cause was a cosmic, ray-induced bit flip. The sun may have literally changed a vote. Don't worry, it was caught in a recount. And then there's radiation exposure in the upper atmosphere. You don't think about it often, but if you're a frequent flyer, especially on polar routes, you've probably received a little dose of space radiation. Not enough to glow, but measurable. During intense solar particle events, airlines reroute flights away from the poles, where Earth's magnetic field offers the least protection. Cabin crew log their hours not just in terms of miles, but radiation exposure limits. You could be sipping tomato juice in seat 17A while the plane gets lightly peppered with protons. It's all part of life in a system bathed in solar fury. And meanwhile, you lie here. No protons punching your neurons. No GPS errors, no plane reroutes. Just the ticking of your inner clock, the rhythm of breath, the low whisper of a planet protecting you with layers of electric silence. It's kind of funny, isn't it, that these tiny particles, smaller than atoms, mostly unnoticeable, can cause such big trouble. That something too small to see can crash a satellite, jam a submarine signal, or rewrite a few thousand lines of mission-critical code. It's like finding out gnats have been untying your shoelaces all day. Of course, not every particle makes it into the atmosphere. Most are deflected by Earth's magnetic field. Those sweeping arcs of invisible force you can't feel, but that shape your entire existence. Some of the particles get caught in the Van Allen radiation belts, trapped in spiraling loops. Others are absorbed into the poles, where they create auroras. Again, the visible bruising of Earth's upper skin. Right now, in places like Iceland or northern Canada, people are standing in snowy fields, gazing up at curtains of green and purple light that ripple silently overhead. They're probably not thinking about the ionosphere. They're not worried about proton events. They're just soaking in the spectacle, unaware of the particle storm breaking above their heads like glass on steel. But you're here, listening, eyes closed, mind open, feeling the strange, surreal beauty of knowing too much and not quite enough. Because that's what the sun does, really. It keeps you alive, yes, but it also keeps you guessing. And those tiny particles, they never stop coming. Auroras aren't just pretty lights. You lie there in the dark, picturing green curtains flowing across a night sky, like ghostly fabric caught in slow motion. Maybe you've seen them in real life. Maybe just in photos, those long exposure shots with glowing skies above frozen lakes, silhouetted trees, or wide-eyed people pointing their cameras northward. Auroras are beautiful. They're ethereal. They're bucket list magic for Instagram pilgrims and stargazers. But let's not kid ourselves. They're also warnings. Not to alarm you, because yes, you're trying to sleep. But when you see an aurora, you are literally watching Earth's atmosphere get punched by space. That serene ripple of color, that's a battle wound. When it's the visible result of solar particles colliding with atmospheric gases at speeds and energies that would otherwise cook you in an instant, if not for the protective magnetosphere you're currently snuggled under. It's like admiring the bruise without asking what caused the punch. Auroras, both borealis in the north and australis in the south, form when high-energy charged particles from the sun spiral down Earth's magnetic field lines and collide with atoms in the upper atmosphere. The energy released in those collisions is what makes the sky glow. Oxygen atoms emit green or red light, depending on the altitude. Nitrogen? That's where you get the purples and blues. And those waves, they follow the lines of magnetic force, curving, fluttering, sometimes pulsing, like wind chimes responding to a storm that's too big to see. Tonight, auroras are dancing unusually far south. Maybe they're touching the Great Lakes, maybe even stretching fingers into northern states like Idaho, Montana, and Maine. That's a sign, a red flag in soft greens and flickering violets. Because the further south they appear, the stronger the geomagnetic storm overhead. Back in 2003, during the Halloween storms, auroras were visible as far south as Florida. People called 911 to report fires in the sky. In 1859, during the Carrington event, there were reports of people in Panama reading their newspapers by the light of the auroras. That's how bright and how intense these things can get. Historians still argue whether ancient myths about burning skies or rivers of fire were inspired by supercharged auroras. Norse legends speak of the Bifrost, a rainbow bridge to the gods. Many believe it was based on the Northern Lights. In Australia, indigenous stories describe auroras as bushfires in the spirit world. Around the globe, people saw these lights and knew instinctively, something is happening. They weren't wrong. Auroras are not just light shows. They're a symptom. To scientists, they indicate strong solar activity. To power companies, they're a call to action. To pilots on polar routes, they're a reason to double-check radiation exposure logs. And to satellite operators, they mean wake-up calls at weird hours and the kind of tension usually reserved for bomb defusal scenes in movies. One of the fringe facts you might like, during strong auroras, ground-based radio transmissions can reflect off the ionosphere in weird ways. In theory, where someone in Ohio could hear a ham radio operator in Finland bouncing their signal off the electrically charged sky. It's called skywave propagation, and some amateur radio enthusiasts live for these moments, when the sun's tantrum opens up the world in unexpected ghostly channels. You, meanwhile, are tucked safely beneath the show. But imagine what it would be like if you could see the full extent of the auroras, not just the pretty part in the visible spectrum. Imagine you had ultraviolet eyes, or could see the X-rays and gamma rays sparking in the upper atmosphere. You'd see a cascade of ionization, a glow more intense and terrifying than any Northern Lights cruise brochure could capture. The sky would look like a wound that never quite heals but flares open when the sun flinches. And here's another thing they don't tell you on those aurora hunting tours. Extreme auroras can mess with animals. There are whispers, some unconfirmed, some semi-documented, of deer stampedes, mass bird disorientations, even dog agitation during extreme geomagnetic storms. Some believe it's the shifting magnetic field. Others think it's infrasound, the ultra-low frequencies emitted during ionospheric disturbances. Or maybe the animals just know what we forget. The lights mean something. Not just beauty, not just wonder, but change, movement, pressure. Still, you can't blame people for staring, for gasping, for pulling over on a country road and just watching. Because even if they don't know exactly what's happening, they feel it. You might feel it too, a kind of electric tug in your chest. Not fear exactly, not awe. Something more elemental, like being reminded that you live in a dome of magnetic tension, spinning under a sun that doesn't always play nice. There are aurora chasers out there tonight, wrapped in scarves, tripods set, batteries pre-warmed, hunting for the perfect still shot of chaos in the sky. They're tracking the KP index, checking aurora forecasts, trading messages about where the skies are clearing. And when the colors appear, silence, wonder. That primal quiet that comes only when humans remember we're standing under something we don't control. But you're not chasing anything. You're floating here, in that warm, sleepy stillness. Just knowing this is happening is enough. That somewhere above you, Earth is glowing with borrowed fire. That the auroras are more than pretty, they're messages. The shimmering postcards from the sun that say, "I'm here, and I'm still bigger than you." And in return, Earth answers, softly, brilliantly, with light. The sun has a pulse. Right now, without realizing it, you're riding a wave. Not an ocean wave, not a mood swing, although fair. This is solar, a slow rhythmic rise and fall of energy so large it spans decades. And you are caught in the middle of its current, humming along on a planet that can't help but bob with every beat. Because the sun has a pulse, it's not a heartbeat in the way yours thumps in your chest, but it is a cycle, a repeating pattern of calm and chaos, roughly every 11 years. Scientists call it the solar cycle, and you're currently inside Solar Cycle 25, which sounds like the name of an indie sci-fi series, but is really just the latest phase in a centuries-old dance of rising and falling solar activity. During solar minimum, the sun is sleepy. Fewer sunspots, fewer flares, quieter magnetic behavior. But when it revs up towards solar maximum, it's like flipping a switch on a celestial pressure cooker. Sunspots multiply, flares grow, CMEs fling themselves into space like solar tantrums, and Earth's magnetic field gets knocked around like a kid's snow globe. And guess what? We're approaching the maximum of this current cycle. Fast. The funny part? We didn't think it would be this intense. Predictions back in 2019 suggested this would be a mild cycle, maybe a little more active than the quiet solar cycle 24, but nothing worth losing sleep over. Well, about that. Solar cycle 25 is flexing harder than anyone expected. Sunspot numbers have consistently overshot forecasts. The sun is throwing out more flares, more proton events, and more geomagnetic storms earlier in the cycle than models predicted. It's like watching someone who said they weren't coming to the party show up in glitter and kick the speakers over. Historians still argue whether earlier civilizations knew about this pattern. The earliest sunspot records date back to the Chinese astronomers of the Han Dynasty. They didn't have telescopes, of course, but during heavy atmospheric dust or at sunrise, it was occasionally possible to spot the darker blotches on the solar disk. They called them black spots on the sun and often interpreted them as omens. By the 1600s, with the invention of the telescope, European astronomers began to sketch and count sunspots more consistently. And one of the first to do so? Galileo. Yes, the Galileo. Still ruining people's worldviews centuries after being excommunicated. Then came 1843, and a German amateur astronomer named Samuel Heinrich Schwabe. He wasn't trying to discover anything revolutionary. He was just trying to find a planet. But instead he noticed that sunspot numbers rose and fell in a regular rhythm, roughly every 11 years. And so, the solar cycle was born. More accurately, our awareness of it was born. The sun's been pulsing like this for billions of years. We just finally noticed. Here's how it works in simple, sleepy terms. The sun's magnetic field flips every 11 years. North becomes south. South becomes north. And the sunspots? They come in waves. More when the field is tangled, fewer when it's smooth. This cycle affects everything. Auroras, satellite health, radio signals, even the thermosphere's density. More solar activity means more upper atmospheric heat, which in turn means more drag on low-orbit satellites. It's all connected, like a cosmic tide pulling every strand of modern technology in and out. You're probably wondering, why does the sun do this? Great question. We don't know. Not really. Solar physicists understand what the cycle is, and some of the internal processes, like the solar dynamo effect, where plasma flow inside the sun generates magnetic fields. But no one fully understands why it ebbs and flows so consistently, or why some cycles are stronger, or why some have two peaks instead of one. Yes, two peaks, like a camel. Some solar cycles, looking at you, cycle 23, don't just build to a single explosive maximum and then fade. They surge, then dip, then surge again. We like the sun remembered it had one more thing to say, which is comforting. Right now, there's some debate over whether cycle 25 will do the same. The numbers suggest we're approaching a peak in mid to late 2025, but there are whispers that we may see a double hump again. That means more flares, more CMEs, more nights like this one, when the sky glows and your phone quietly glitches and you don't realize the sun is breathing down your neck. Fringe side note, there are long-term solar cycles too. Like the Gleisberg cycle, approximately 88 years, or the Suez cycle, approximately 200 years. These are patterns layered over the 11-year one, and they seem to govern grander phases of solar intensity and calm. Some scientists even speculate that a super maximum might be due in this century. That's a fun thought, huh? So here you are, drifting towards sleep, carried gently on the solar tide. Tonight's storm, a product of this rising cycle, those auroras a few hundred miles north. Another heartbeat, the jittery GPS signal, the sudden static on a transatlantic radio, all just echoes of the sun's magnetic blood moving through the solar system. You feel small, maybe, but not insignificant. Because if nothing else, understanding this rhythm connects you to something massive, something that breathes not in seconds, but in decades. And you're a part of that story. So rest now. The sun will rise in the morning. It always does. But the space between now and then, that belongs to the pulse, that quiet magnetic rhythm of the star that made you. And tonight, it's quickening. Sleeper tech at risk. You sleep like everything is fine. Your phone is charging on the nightstand. Your fridge is quietly humming. Your router glows softly in the corner like a nightlight for your Netflix habit. Somewhere overhead, a satellite is triangulating your exact location with absurd precision. And deep under the ocean, data pulses through fiber optic cables like blood through veins, carrying your emails, your memes, and your slightly regrettable online purchases. All of it depends on technology. And all of that technology, it depends on the sun not having a really bad day. Because while you're wrapped in flannel and dreams, a surge of charged particles from the sun, just the right kind, just the right direction, could sweep through space and knock out entire systems without even trying that hard. We're not talking science fiction. We're talking about real, known vulnerabilities. You don't need a Carrington-class event to cause chaos. A mid-range geomagnetic storm, like the one brewing right now, is enough to make people at power stations and telecom companies very nervous. The power grid, for starters, is basically a giant antenna. Long transmission lines stretch across thousands of miles, acting like receivers for geomagnetically induced currents, GICs. These are slow, powerful electric flows generated when the Earth's magnetic field fluctuates. During a storm, those lines can start to carry current they weren't designed for. Transformers overheat, protective relays trip, entire regions can go dark. In 1989, Quebec learned that lesson the hard way. But that was a relatively simple grid. Today, our electrical infrastructure is far more interconnected and far more fragile. Historians still argue whether modern utilities take the risk seriously enough. Some say we've hardened the grid. Others point to reports showing just how many key transformers are still unshielded and decades old. And when you realize some of those transformers take a year to replace, yeah, it gets real pretty fast. And then there's GPS. Oh, sweet, humble GPS. Used for everything from guiding planes and ships to telling you which lane to be in during a late-night Taco Bell run. During geomagnetic storms, the ionosphere becomes turbulent. GPS signals, which travel through this layer, start to refract unpredictably. The result? Position errors, timing glitches, and, if the storm is strong enough, total loss of signal. A GPS outage doesn't just mean your Maps app freaks out. It means cargo ships go off course. Precision farming tools stop working. Emergency services lose location data. Stock exchanges, one which rely on GPS for nanosecond accurate timestamps, could be thrown into chaos. Even your phone's ability to tell time might quietly go out of sync. And it's not just above ground. You might think fiber optic cables buried deep beneath the oceans are immune to solar shenanigans. The cables themselves are safe. They're glass, not metal. But the repeaters, the electronic devices placed every few dozen miles to boost the signal, are very much vulnerable to GICs. A powerful enough storm could, in theory, disrupt or damage the amplifiers in a major transatlantic cable. That's not, oops, the Wi-Fi's down. That's, oops, half the internet traffic between continents just vanished. Fringe theory time. In 2021, a team of researchers modeled what would happen if a solar superstorm hit today, and their simulations suggested that the internet might be more vulnerable than the power grid, especially if key undersea cables were knocked out. The cascade effects, disrupted cloud services, offline banking, social media blackouts, a return to the dark ages of actually having to talk to people in person? Shudder. But it gets weirder. Modern airplanes rely heavily on satellite communications and GPS. During geomagnetic storms, transpolar flights are sometimes rerouted to lower latitudes to avoid radiation exposure and communication loss. The FAA has guidelines for these situations. Pilots are trained. But still, during a strong enough event, planes could lose both high-frequency radio and GPS simultaneously. That's why they carry backups, and why their uniforms include more than one metaphorical seatbelt. Your car? Your smart fridge? Asha, your voice assistant that can't pronounce your name right? They all rely on delicate webs of communication, timing, and location. Most of them are built assuming that Earth's magnetic field is a fixed, stable thing. But it's not, and it's currently being nudged, pressed, and distorted by charged particles traveling faster than anything else you'll encounter in your daily life. Right now, engineers are watching dashboards that look like something out of a video game. Graphs showing geomagnetic K indexes, satellite charging risk levels, power grid fluxes. They're watching for the moment things tip from interesting to bad. And most people? Most people just keep scrolling, totally unaware. You're one of the lucky ones. You know what's happening. You're not panicking. You're just aware that while you rest, a storm is tugging gently at the seams of modern life. Nothing might break tonight, but the seams are there. There's a beauty to that fragility, isn't there? The idea that we built this entire civilization on the assumption that the sun will behave, and when it doesn't, the lights flicker, the planes reroute, the satellites forget their names, and somewhere in a server farm, a machine that's never known darkness finally does. But even then, the world keeps turning, because systems reboot, satellites recalibrate, engineers shake their heads, mutter about solar cycles, and do it all again the next time. And you? You roll over. Let the gentle hum of distant servers lull you. Dream of auroras and power lines glowing like ley lines in the sky. And trust, just a little, that we've learned enough to hold it all together, at least for tonight. Out of flight plans and polar peril high above your head, so high you'd need a ladder made of jet engines and questionable airline peanuts, someone is flying over the Arctic Circle right now. They're not thinking about the sun. They're focused on headings, fuel levels, crosswinds, and whether that coffee was actually decaf. But behind the scenes, something invisible is pressing on their reality. Because flying near the poles during a geomagnetic storm, it's not just cold, it's complicated. You see, Earth's magnetic field is strongest and most stable around the equator, but up near the poles, it gets twitchy, like a bad mood with altitude. And tonight, with solar particles streaming in and Earth's upper atmosphere all stirred up, that twitchiness is climbing toward a boil. Polar routes, those long-haul flights that slice across the top of the globe to shave time off the journey, are especially vulnerable during geomagnetic storms. Why? Because when the sun starts flinging radiation toward Earth, most of it is deflected by the magnetosphere toward the poles. That's where the shield is weakest, and where solar particles sneak in like VIP guests with fake badges. Now imagine your plane is flying right through that particle party. That's why, on nights like this one, flight paths get changed. Polar flights can be diverted toward mid-latitudes, or grounded entirely if the storm is strong enough. You might never notice it. The pilot might never mention it. But air traffic control and space weather teams have been quietly arguing over your flight plan for hours. Historians still argue whether cosmic radiation from solar storms has ever caused in-flight incidents. There's no confirmed case of a plane crashing due to a solar event, but radiation levels do spike in the upper atmosphere, especially during high-latitude flights. That's why pilots and cabin crew track cumulative exposure over time. Because yes, flying too much can actually be a radiation risk. During an average transpolar flight, passengers receive a radiation dose similar to a chest X-ray. Not dangerous for a one-off, but stack up hundreds of flights a year, and it adds up. That's why the International Commission on Radiological Protection classifies airline crew as radiation workers. That's a real thing, like nuclear plant technicians, but with worse sleep schedules. And solar storms? They're radiation jackpots. In the worst-case scenario is what scientists call a solar proton event, SPE. This is when the sun launches a flood of high-energy protons that slam into the atmosphere. They're rare, but when they happen, the radiation dose for polar flights can triple or more. The FAA monitors these events constantly. If one flares up, flights get rerouted fast. Right now, space weather alerts are probably active. Pilots flying transpolar routes, say New York to Hong Kong or Chicago to Dubai, are tracking radiation data as part of their regular protocol. Some aircraft may have shifted routes down through Europe or even hopped westward across the Pacific instead. Longer flight, more fuel, but safer skies. And it's not just radiation. During geomagnetic storms, high-frequency, HF, radio communication can vanish entirely in polar regions. That's the kind of radio used for communication beyond line of sight. Before satellites, it was how planes talked to ground control across oceans and ice. Even today, HF is still a vital backup. But during a solar storm, the ionosphere can go nuts. Signals bounce unpredictably or get absorbed completely. It's called a polar cap absorption event, and it basically silences the airwaves above the Arctic. Pilots have backup systems, but when your primary and secondary comms start glitching 39,000 feet over a frozen wasteland, it gets uncomfortable real fast. You might be wondering, do passengers feel any of this? Not usually. You might experience some turbulence. Maybe a slightly longer route. Maybe your in-flight Wi-Fi goes down, and you chalk it up to airline incompetence. But in the cockpit, there's a quiet dance of adjustments. Reroutes, radiation logs, comm system checks, all playing out while you sip orange juice and fight with the tray table. Fringe fact for your next trivia night: Concorde, the supersonic jet of the 70s and 80s, actually flew high enough to get close to dangerous radiation levels during solar storms. British Airways and Air France monitored space weather closely and would delay or ground flights during elevated solar activity. Turns out, when you're flying twice the speed of sound, you're also flying right into the edge of the sun's wrath. Even the International Space Station isn't immune. During strong solar events, astronauts move to shielded areas of the station, usually the storm shelter, built into the water storage and thicker walls of specific modules. They don't stop floating. They don't panic, but they do take cover, just in case. So here you lie, grounded and calm, while the sky above is quietly rearranging its travel plans. Somewhere right now, a pilot is adjusting a heading. A controller in Anchorage is updating a radar track. A flight planner in Frankfurt is checking auroral forecasts against transatlantic air corridors. And above them, invisible fingers of charged particles are threading through the polar sky like aurora-colored lace. You don't need to worry about it. The systems are in place. The protocols are solid. But it's a reminder, even in our age of jet engines and glass cockpits, the sun still gets a vote. And sometimes it votes nope. You settle deeper under your covers, grounded, safe, watched over by all the invisible layers of protocol and practice, satellites and sensors, that make flight over the top of the world possible, even when the sky's having a bit of a meltdown. So if you dream of flight tonight, imagine not just the wings in the clouds, but the glowing particles arcing over the poles, the silent storms above the storms, the pilots threading their way through them, and Earth doing its best to keep everything flying steady, even when the sun disagrees. The strange case of the shrinking thermosphere. You drift on the edge of sleep while above you, far, far above you, the very edge of Earth's atmosphere is doing something odd. It's shrinking, not in a cartoonish, whoops, it's disappearing way. There's no cosmic vacuum cleaner hoovering up sky, but something real, measurable, and faintly unsettling is happening. The thermosphere, that outermost atmospheric layer where satellites orbit and auroras dance, is quietly thinning, collapsing downward, like a balloon losing air in slow motion. And scientists, they're not totally sure why. Let's take a quick elevator ride up. The thermosphere begins around 80 kilometers, 50 miles above the Earth, and stretches out to about 600 kilometers, 375 miles. This is space-adjacent real estate, the domain of the International Space Station, low Earth orbit satellites, and the glow trails of re-entering debris. It's also the part of the atmosphere most sensitive to solar activity. When the sun is rowdy during solar maximums, the thermosphere swells with heat and energy. Think of it like a hot air balloon catching a flare. If the increased ultraviolet and X-ray radiation from the sun energizes this layer, making it expand outward. This expansion increases atmospheric drag, which sounds annoying, but is actually good for controlling space junk. It helps old satellites and debris deorbit faster. But during solar minimums, or when something weird is going on, the thermosphere cools. It contracts. And that's exactly what scientists noticed in the late 2000s. Between 2007 and 2009, the sun entered one of its quietest phases in more than a century. Solar activity plummeted, flares vanished, sunspots were rare, and the thermosphere, it deflated like a tired beach ball. Satellite observations showed a dramatic drop in density at orbital altitudes, much more than models had predicted. It wasn't just low activity, it was record-breakingly low. Historians still argue whether similar shrinkages occurred in previous solar minima, like the Maunder minimum in the 1600s. But we didn't have satellites then. We barely had telescopes. So for now, this recent anomaly remains one of the strangest puzzles in solar terrestrial physics. Why does it matter? Because satellites rely on thermospheric drag to naturally slow down and deorbit when they're no longer useful. A thinner thermosphere means less drag, which means old satellites hang around longer than they're supposed to, and so does space junk. Right now, Earth's orbit is a crowded mess of objects. Active satellites, dead ones, tools dropped by astronauts, shards from past collisions. There's even a frozen spatula up there, courtesy of a shuttle EVA in 2006, no judgment. Normally, these things decay in orbit and burn up harmlessly in the atmosphere within a few years. But when the thermosphere is thin, that process slows to a crawl. Instead of re-entering in 5 years, an object might take 50, or not come down at all. And that increases the odds of collisions, which generate more debris. It's called the Kessler syndrome, a runaway chain reaction of crashes and fragmentation that could, in theory, make certain orbital bands too dangerous to use. Imagine trying to drive a car through a highway filled with glass shards, broken axles, and unmanned bicycles, all traveling at 17,000 miles per hour. That's what space agencies are worried about. Now the thermosphere is thickening again. As solar cycle 25 ramps up, the sun's energy is heating the upper atmosphere, and satellite drag is on the rise. But the memory of that deep contraction hasn't faded because it raised deeper questions, like whether human activity could also be affecting this layer. Some studies suggest that increased carbon dioxide in the lower atmosphere, the stuff causing global warming, might be leaking upward. In the thermosphere, CO2 doesn't trap heat, it radiates it away. So oddly enough, the same gas that's warming the troposphere might be cooling the thermosphere. That's one of those weird science moments that breaks your brain just a little. Fringe Theory Corner. Some researchers wonder if solar grand minima, those multi-decade quiet periods, could permanently alter atmospheric structure. Could a deep, prolonged solar slump change our sky's shape for centuries? Would it affect orbital dynamics, radio propagation, climate patterns? We don't know. But it makes you look up just a bit more thoughtfully. As you lie here, Earth's thermosphere is reacting in real time to solar input. Right now, with geomagnetic activity climbing, it's expanding again. Satellites are experiencing slightly more drag. Space debris is being gently tugged downward. The sky is getting thicker, but only in the most delicate, whisper-thin way. You'd never notice, but a satellite might. That weather satellite you checked earlier today? It likely adjusted its position this week due to shifting atmospheric drag. That navigation satellite your phone relies on? Its operators ran a model of thermospheric density changes due to the flare that erupted 4 days ago. All of it is interconnected. Sun, sky, steel. Even the auroras are part of this. Remember, when particles slam into the thermosphere, they don't just light it up, they heat it. In fact, auroral heating is one of the primary drivers of thermospheric expansion during storms. Every flicker of green light above Iceland or Alaska is also a localized hot flash in Earth's outer skin. And the sun doesn't just stop there. It affects thermospheric chemistry, ion ratios, wind patterns. It's like an invisible hand constantly shaping the top of the world. And you're resting in the quiet beneath it all. The lower atmosphere is calm. The stars are distant, but far above your sky is stretching and flexing with energy from a star you've never touched, but that you know deeply in your bones. You feel the expansion, even if you don't name it. You feel the changes, even if you don't see them. And you sleep unknowingly in sync with a sky that never stops reshaping itself. So dream of thinner skies and distant satellites. Dream of the edge of air, where gravity lets go and solar storms still find their way in. Dream of a thermosphere that holds up the edge of the world, even when it's shrinking, especially when it's shrinking. The forgotten sky of 774 AD. Somewhere in a monastery in 8th century Japan, a monk pauses mid-scroll, looks out the window and sees a sky so red it stains the hills like blood. No fireworks, no armies, no fire on the horizon. Just a silent, glowing dome above the earth. Beautiful, terrifying, and completely inexplicable. He writes it down. In 774 AD, something happened to Earth. Something strange, powerful, and still not fully understood. And unlike the Carrington event of 1859, this one left no sparks on telegraph lines, no failed satellites, no confused power plant workers. Because back then, none of those things existed. But it left a fingerprint. In fact, it left millions of them, hidden in tree rings. That year, there was a sudden, sharp increase in carbon-14 levels in trees all over the world. Carbon-14, or radiocarbon, is produced when high-energy cosmic radiation slams into the upper atmosphere and alters nitrogen atoms. Normally, this process is pretty stable. But in 774, the levels spiked dramatically, about 20 times higher than normal background variation, which is bananas. This wasn't just a blip, it was a cosmic anomaly. Trees in Germany, Japan, the US, all recorded the same sudden boost in atmospheric carbon-14. For a brief moment in time, The Earth was bathed in radiation from something big, and we still don't know exactly what. Historians still argue whether the 774 event was caused by a massive solar storm, a CME of Carrington class or greater, or something even more exotic, like a gamma ray burst from a nearby star. The debate's been going on since the carbon-14 data was first analyzed in 2012, more than 1,200 years after the event. Let that sink in. The trees knew before we did. If it was a solar superstorm, and the auroral records from East Asia suggest it might have been, then it was the most powerful known in recorded human history. More powerful than Carrington, more intense than anything in the satellite era. And humanity, it survived it by sheer dumb luck. No electronics, no power grids, no spacecraft, just farmers, scribes, and monks looking up at a sky they couldn't understand and writing down what they saw. And some of the records from that time describe a red crucifix in the sky. Others mention a second sun or a ghostly fire above the earth. It's hard to interpret exactly. Ancient language mixes science, religion, and metaphor like stew, but the consistency is chilling. And that carbon-14 spike? Not the only one. A second, smaller spike shows up in tree rings, dated around 993 AD. A similar event, less intense but still far above background radiation. Two cosmic surprises in the span of a few centuries. Both mysterious, both invisible, except for the marks they left in living wood. That's the thing about space weather. It doesn't need a satellite to crash into. It will leave evidence wherever it touches, in rings of trees, in layers of polar ice, in human stories whispered down through generations. Tonight, those trees are still standing somewhere. Maybe not the same ones, but their descendants. Their cellular memories carry the data of that ancient storm. And if you sliced one open and looked, really looked, you'd see the thin, dark ring of 774, the year the sky went red and the earth changed. Fringe fact for your midnight mind. Some scientists wonder whether these ancient radiation events could have influenced evolution. Sudden spikes in radiation might cause rare genetic mutations, microscopic edits to the DNA of living things. Probably harmless, possibly world-changing. The idea that a solar event, or a cosmic burst from a star we've never named, could have nudged life along a new path? That's the kind of thought that makes you sit up straight in the middle of the night and whisper, huh. And then there's the other theory, the unsettling one, that if the 774 event was a solar superstorm, it means our sun is capable of flinging far more powerful CMEs than we've observed in the modern era. That Carrington wasn't the worst. It was just the worst we remember. If that's true, the question isn't if it'll happen again. It's when. And will we be ready? Because while you lie here beneath satellites and power lines, those carbon-14 spikes remain a quiet, tree-ring warning from the past. A signal that once the sun flexed harder than we imagined, and Earth took the hit. You'd think this would keep people awake at night. It doesn't. Not really. It's too abstract, too ancient. But it's there, etched into wood, into ice, into stories. Waiting for someone to notice. Waiting for someone like you. So you close your eyes and imagine that sky from 774. No artificial lights, no noise pollution. It's just a sea of stars and then color, fire, light. The air itself glowing red like a slow, silent alarm. And then darkness. Because whatever it was, it passed. Earth rotated. The sun calmed down. The sky went back to blue. And the monks returned to their scrolls. Still, the trees remember. And so now do you. Sunlight with a side of gamma. You feel it every morning, that gentle golden warmth slipping through the window, curling against your face like a cat in search of your attention. Sunlight, friendly, reliable, life-giving. But underneath the glow, beneath the UV rays that bronze your skin or betray your trust with a surprise sunburn, lurks something less polite, something rarer, stranger, potentially dangerous. Gamma rays. Yes, gamma. the same category of radiation responsible for comic book origin stories and nuclear fallout zones. As the sun doesn't blast you with them daily, thankfully, but on occasion, during certain types of solar eruptions, it sneaks a few into the light stream. Just a little bonus seasoning on your photons. And this right here is where solar science gets delightfully weird, because the sun, as friendly as it seems, is also a fusion reactor. Deep in its core, hydrogen is being smashed together to make helium, releasing tremendous amounts of energy in the process. Most of that energy takes thousands of years to travel from the sun's core to the surface. But gamma rays? Those are born down deep and then get degraded, slowed, stretched, and softened into visible light by the time they reach you. So how are we getting fresh gamma rays during solar storms? That's where solar flares come in. These are sudden bursts of energy in the sun's atmosphere, usually near sunspots caused by magnetic reconnection. Twisted magnetic fields snapping and rearranging like cosmic rubber bands under tension. When this happens, particles get accelerated to near-light speeds. And when those supercharged particles collide with heavier ions or smash into the sun's dense lower layers, boom, gamma rays. Not the kind that'll fry you instantly, but intense enough to be detected all the way out here. In fact, NASA and ESA satellites often pick up gamma-ray signatures just minutes after a major solar flare. These gamma emissions don't pose a serious threat to people on the surface. Earth's atmosphere does a solid job absorbing and deflecting them. But astronauts, aircrew on polar routes, satellites, different story. You might be asking, okay, but how much gamma are we talking? Not a ton. And these aren't continuous beams of death, but rather short-lived pulses, sometimes seconds, sometimes minutes. However, they serve as a clue that something big just happened. Gamma rays are usually accompanied by X-rays, protons, and high-speed electrons. Basically, if the sun sends gamma rays your way, it's yelling in all frequencies. Historians still argue whether solar gamma events have ever impacted ancient life in meaningful ways. Could a sudden increase in atmospheric ionization, driven by a flare, have altered cloud formation or disrupted animal migration? There's speculation, but the evidence is faint, like whispers from millennia ago trapped in ice. There's also the question of superflares. We've never observed one from our sun in modern times, but stars similar to the sun have been seen erupting with flares hundreds or thousands of times more powerful than anything we've recorded. If our sun did release a superflare, it could emit gamma radiation powerful enough to temporarily alter the upper atmosphere, jam satellites, and potentially harm astronauts in space or passengers on high-latitude flights. The good news? It's unlikely. The bad news? Unlikely doesn't mean impossible. Fringe idea for the curious. Some researchers have speculated, quietly and usually with lots of disclaimers, that a solar superflare might explain events like the 774 AD carbon-14 spike. No hard proof. Just tantalizing data in a sky full of questions. And gamma rays? They're part of that puzzle. Because when we detect them, we know the sun isn't just flaring, it's accelerating particles to relativistic speeds. That's not just fireworks. That's physics on a scale humans can barely simulate. The kind of energy that makes particle colliders look like electric toothbrushes. It's a reminder that the sun doesn't just glow, it detonates, quietly, repeatedly, and sometimes with a side of gamma. Tonight, right now, as you listen, there are detectors in orbit, Fermi, RESI, rest its mission, and others watching the sun's activity in gamma and X-ray wavelengths. They're tuned to listen for the snap and crackle of solar magnetic fields losing their temper. And if the sun flares hard enough, those detectors will catch it. And down here, you'll feel nothing. No pulse, no sting, no tingling skin. The atmosphere does its job, and you sleep on. But high above, our satellites brace. The ISS crew double-checks radiation monitors, and air traffic controllers on polar routes quietly consider rerouting flights, just in case. So if the sun ever throws a truly monstrous tantrum, one of those once-in-a-millennium superflares, we won't see it first. We'll detect it in gamma, in X-rays, in protons streaming toward Earth at unthinkable speed. And Earth will brace itself. The upper atmosphere will flash. The magnetosphere will shudder. Communications will ripple, and your phone might lose signal for a while. Then it'll come back. You'll open your weather app. You'll check the sky, and you'll think, bright out today. Not knowing that sunlight arrived carrying a secret, trailing the faintest kiss of gamma behind it. So now, as you lie still and quiet, under a night sky that hides more than it shows, and remember this, even your warmest star has teeth, ancient eyes on solar fire, long before satellites orbited Earth and long before Galileo squinted through a telescope and thought, that looks wrong. Humans were already watching the sun. You can picture it, can't you? A Sumerian priest standing on a stone platform, eyes narrowed, stylus in hand. Or a Chinese court astronomer etching symbols onto bamboo slips as the sun rises, unusually dark. They didn't have filters or math, but they saw. Because the sun doesn't always hide its moods. Sometimes it leaves marks. Literally. Clay tablets from Babylon around 600 BC contain the first recorded observations of what we now think were sunspots. Ancient scribes wrote of black dots, or blemishes, seen on the solar disk at dawn or dusk, when the sun's glare was low enough to allow brief, no unaided observation. These early sky watchers weren't sure what they were seeing, but they knew it meant something. And in ancient China, solar monitoring was an institution. Imperial astronomers in the Han Dynasty, circa 200 BC, kept meticulous records of strange sky phenomena. They logged black spots on the sun, fire stars, heavenly vapors, and dragons in the sky. We now interpret many of those as sunspots, flares, or auroras. Even back then, people seemed to understand, intuitively, fearfully, that when the sun acted strange, so did Earth. Historians still argue whether these early records were purely observational or if they were already starting to see patterns. Some scholars believe ancient Chinese astronomers recognized cyclic behavior in solar blemishes. That would make them the first unofficial sun cycle trackers, beating modern science by almost 2 millennia. And then there are the auroras. Northern peoples, the Sami of Scandinavia, the Inuit, the Cree, have stories that stretch back before writing. The lights in the sky weren't lights. They were spirits, omens, messages. In Norse mythology, some believed auroras were the reflections of Valkyrie armor as they rode to collect the fallen. Across the Pacific, in ancient Japan, there are descriptions of the sky burning red like blood. Some of those records may correspond with powerful solar events. Remember the 774 AD anomaly? There's a Japanese chronicle that mentions a mysterious sky glow around that time. Coincidence? Or a glimpse of the same radiation storm that left its signature in tree rings? Even medieval Europe, and not exactly known for its scientific rigor, occasionally paused to document strange lights in the heavens. Illuminated manuscripts show fire in the sky, often interpreted as divine signs. Monks and kings didn't know about the solar wind, but they understood awe. Fringe fact, a few researchers believe that some famous ancient battles may have been delayed or influenced by auroras. One account claims Roman soldiers hesitated to march under a blood-red sky, fearing it was an omen of death. Can't prove it, but it's not hard to imagine a superstitious general glancing upward and thinking, maybe tomorrow. And speaking of delays, stone carvings in Peru, Mayan codices, and even petroglyphs in the American Southwest show swirling symbols that some have interpreted as sunspot-inspired or aurora-related. Again, speculative. But human brains love patterns, and when the sky changes dramatically, someone always draws it. Which brings us to one of the most haunting mysteries of ancient solar observation, the 17th century Maunder minimum. From about 1645 to 1715, sunspot activity vanished. Astronomers, now equipped with telescopes, were tracking sunspots with growing accuracy. And then, almost nothing. Decades passed with the sun appearing oddly, eerily smooth. At the same time, parts of the Earth experienced what came to be known as the Little Ice Age. Colder winters, failed crops, glaciers advancing. Is there a link? Probably lower solar activity likely reduced the total solar irradiance hitting Earth's surface, just enough to tweak weather patterns. Not a Hollywood-style freeze, but enough to make history shiver. Historians still argue about causality, whether the Maunder minimum caused the Little Ice Age or simply coincided with it. But the timing is suspicious, and it makes you wonder how many of Earth's great shifts have been quietly triggered by a sun in retreat. Tonight, somewhere, a backyard astronomer is pointing their scope at the sun's limb, with a proper filter, of course, counting sunspots. Maybe they're a teenager in Montana, maybe a retired engineer in Osaka. They're part of a global tradition, amateur observers who track the sun like it's a stock market. And when they see a new sunspot emerge, when that dark patch curls into view, they're seeing the same phenomenon that once puzzled Babylonian priests and Chinese scholars: a magnetic snarl, a sign of pressure, a warning that the star is about to speak. And not everyone has forgotten these ancient observations. Solar physicists still reference medieval chronicles, especially when trying to match tree ring data or polar ice core samples to historical flare events. There's even a dedicated field, historical climatology, where scholars and scientists pore over old documents looking for celestial breadcrumbs. Because history isn't just wars and kings, it's sky, it's patterns. And sometimes the key to the future is written in the past, etched into clay, scratched onto bone, whispered by starlight. And you're part of that lineage. Maybe not with a stylus or a robe, but with awareness. You know now, as you lie here blinking at the ceiling, that the sun has always been watched and has always watched back. It changes things, doesn't it? Want to know that the glow warming your face in the morning has been studied for thousands of years, that it has moods and secrets, that people far older than you once looked up in wonder, confusion, and fear, and wrote it down. So if you dream tonight of dragons in the sky, of black dots on a golden disk, of silent scrolls and shimmering spirits, know this: you're not imagining, you're remembering. The Goldilocks magnetic reversal. You stretch, you sigh, you sink deeper into stillness. But under your feet, Earth is already shifting. Not the ground exactly, not the plates or the mountains. It's deeper, slower, stranger. It's the magnetic field. And one day, not today, but someday, north will become south, and south will become north. Because Earth's magnetic poles flip, and not just once or twice. They've done it many times. Like clockwork, but on a clock whose hands move in millennia. It's called a geomagnetic reversal, and it happens when the molten metals churning in Earth's outer core, those iron-rich rivers that generate our magnetic field, rearrange themselves in such a way that the field begins to weaken, fragment, and then eventually flip entirely. The process can take thousands of years, or it can start fast and then linger, like a stubborn download stuck at 99%. Right now, you're living in what scientists call a normal polarity epoch. Magnetic north is roughly near the geographic North Pole, but every so often, about every 200,000 to 300,000 years on average, Earth switches polarity. The last time it happened was around 780,000 years ago, which means we're overdue. But don't panic. Magnetic reversals are not instant, apocalyptic, all electronics die scenarios. They don't flip like a coin tossed into the void. The field doesn't suddenly vanish. It just weakens, becomes unstable, and reorients over time. Still, while you sleep peacefully now, the implications for modern technology during even a partial reversal are very real. When the magnetic field weakens, and it does during these transitions, Earth becomes more vulnerable to solar radiation. The magnetosphere thins. More cosmic rays reach the surface. The Van Allen belts, which trap high-energy particles, shift in shape and intensity. And guess who notices first? Satellites, astronauts, animals, and eventually, us. Historians still argue whether past magnetic reversals have had biological consequences. There's no definitive evidence of mass extinctions lining up precisely with flips, but the fossil record has some suspicious coincidences. Some paleontologists point to minor die-offs, radiation-linked mutations, or increased evolutionary branching around reversal periods. Imagine your ancestors, early humans or their primate cousins, looking up at a sky they couldn't explain, bathed in just a little more ultraviolet, a little more cosmic static. Maybe it nudged the species forward. Maybe it just made sleeping harder. Now here's the weird part. The magnetic field has been acting twitchy. In recent decades, Earth's magnetic north has been drifting faster than usual, moving from northern Canada towards Siberia at a pace that has scientists double-checking their maps and satellites reconfiguring their guidance systems. The field is also weakening overall, especially over a mysterious zone known as the South Atlantic Anomaly, an area where the magnetosphere is oddly thin, exposing satellites to higher levels of radiation. You probably haven't heard of it, but spacecraft engineers have. They design instruments to shut down or shield themselves while passing through that region. It's like flying through an invisible storm that only electronics can see. So, is this the start of a reversal? Maybe, maybe not. The truth is, scientists don't fully understand the mechanisms behind magnetic flips. We can model them. We can measure their fingerprints in lava flows and seabed sediments. But predicting the next one? That's like trying to predict the next sneeze of a sleeping giant. Fringe theory moment. Some researchers speculate that a full reversal could temporarily break Earth's magnetosphere into multiple north and south poles scattered across the planet, like a drunken game of magnetic twister. Imagine compasses spinning, auroras blooming in places like Rome or Cairo, and radiation exposure increasing at lower latitudes. Would the internet survive? Probably. But satellite systems would be under serious strain. GPS accuracy would falter. Aviation routes would need to change. The global electrical grid, already vulnerable to solar storms, could face more intense bombardment. And then there's the wildlife. Birds, whales, turtles. Many species navigate using Earth's magnetic field. What happens to them during a reversal? Do they get lost? Do migratory paths change forever? Some lab studies suggest animals can adapt over time. Others hint at confusion, hesitation, or strange behavior during periods of magnetic instability. You might not feel it directly, but the world around you would. Slowly, steadily, over decades and centuries, Earth's magnetic identity would shift, and humans, wired as we are for stability, would have to follow. But here's the twist. Despite all this uncertainty, Earth has survived countless reversals. Life kept evolving. Volcanoes kept erupting. The sun kept rising in the east, even if magnetic compasses insisted otherwise. There's no record of the planet catching fire or society collapsing just because the poles swapped dance partners. It's a Goldilocks system in a way. Not too stable, not too chaotic, just unpredictable enough to keep us humble. And tonight, the poles are still where they've been. For now, your compass still works. Your GPS still pings. Your phone still knows which direction is north, give or take a few degrees. But far beneath your feet, in a liquid core thousands of kilometers down, the seeds of a flip may already be swirling, magnetism realigning, polarity prepping, and above you, the sun doesn't really care. Historians still argue whether the sun notices Earth's magnetic reversals at all. Some models suggest it could alter how solar wind interacts with the planet or change where auroras appear. But for the sun, Earth is just one more rock with a light magnetic wrinkle. It flares, it storms, it pulses regardless. So while you dream, know this. Your planet is a compass in motion, a field in flux, and one day the directions you know may turn inside out. But for now, north is still north, south is still south, and everything in between. That's where you are, wrapped in warmth, drifting through the silence of a sky waiting to change. Is the sun getting weirder? You wouldn't think it by looking at it, just a glowing dot in the sky that hasn't missed a shift in over 4 billion years. But lately, the sun has been acting a little odd. Nothing dramatic. No fireballs flung into space like beach balls at a rock concert. No sudden expansion into a red giant that consumes Earth like a snack cake. Don't worry, that's still about 5 billion years away. But if you ask the scientists, the ones sitting quietly in observatories and staring at magnetograms until their eyes cross, they'll tell you the same thing. Something isn't quite lining up. Let's start with the current solar cycle. Solar cycle 25. It was supposed to be mild, predictable, just a light pulse between the more powerful rhythms of solar history. And at first, it was quiet, sleepy, almost boring. Then the sun hit the gas. Sunspot numbers surged earlier than expected. Flares began erupting more frequently. Coronal mass ejections started stacking up like bad weather reports. And the KP index, the scale we use to measure geomagnetic storm activity, has been flirting with storm watch more nights than not. Historians still argue whether we've seen similar curveballs before. Some point to solar cycle 19 in the 1950s, an absolute beast of a cycle that blasted Earth with some of the most intense solar storms ever recorded. Others remind us that the sun is notoriously hard to model. It's not a machine. It's plasma wrapped in magnetism, stirred by nuclear fusion, and laced with mysteries. But even with all that history, Cycle 25's behavior has raised eyebrows. It's not just active, it's uneven. We've had clusters of sunspots in places they're not usually expected. Some flares have occurred without the usual magnetic warnings. And the frequency of dual CMEs, back-to-back ejections riding each other's wake, has gone up. In December alone, Earth was hit with 3 separate moderate geomagnetic storms within 10 days. That's not unheard of, but it's rare outside of maximum phase. And yet, here we are. So, is the sun changing? Well, technically, yes. It's always changing. The sun is a dynamic sphere of gas with no solid surface, constantly roiling, twisting, and occasionally coughing out enough energy to light entire planets on fire. But the question is whether its overall behavior is drifting from the patterns we've come to expect. And there's reason to think, maybe. For one, we've only been watching the sun in detail for about 400 years, and with modern instruments for maybe 70. Phew, that's nothing in stellar terms. Our entire database of normal solar behavior could be just one chapter in a much weirder book. Fringe Theory Corner. Some solar physicists are starting to suspect that we may be entering a transitional phase in the sun's long-term activity, a period of instability that could eventually lead to either a grand maximum or a grand minimum. Basically, either the sun gets louder for centuries or it goes into hibernation. Neither option is fully understood. A grand maximum might mean more frequent superflares, more radiation storms, more auroras in the tropics, sure, but also more stress on satellites, grids, and aviation. A grand minimum, like the Maunder minimum of the 17th century, could result in a long period of reduced solar output, cooler global temperatures, or possible disruptions to atmospheric circulation. You probably wouldn't notice it at first. The sky would still be blue, the sunsets just as smug. But behind the scenes, the sun's pulse would be shifting. And if it swings too far in either direction, Earth will feel it, not as apocalypse, but as a slow pressure that alters climate, technology, and behavior over generations. Back to now. In addition to the sunspot surprises, scientists have also noted an uptick in stealth CMEs. These are coronal mass ejections that launch without the usual warning signs. No obvious flare, no sunspot eruption, just a sudden expulsion of plasma and magnetism that sneaks out like a kid skipping curfew. One such stealth CME hit Earth in 2022 and caused an unexpected G3 class storm. Power grids adjusted, satellite operators scrambled, and an aurora spilled over into latitudes that hadn't seen them in decades. It wasn't catastrophic, but it was humbling. The idea that our best instruments missed it? A little unsettling. And this brings us to the real heart of the weirdness: prediction. We like to think we've got the sun figured out, that we can track its moods, anticipate its flares, and guard ourselves against its tantrums. But increasingly, solar weather forecasts are starting to resemble terrestrial ones. Accurate-ish, prone to surprises, and always about 15% off when you actually need them to be right. Because the sun doesn't run on our schedule. Its surface shifts constantly. Magnetic loops form and collapse in seconds. Deep inside, massive flows of plasma, called meridional flows, move energy from equator to pole and back again in patterns we still can't fully map. Some theories suggest these flows may be changing, slowing, reversing. And if that's true, then the sun may be entering a new era, one with different rules. Not better, not worse, just different. So what does this mean for you, lying here now under your dim light, scrolling your phone or listening to this with one ear tuned to the wind outside? It means you're alive during a time when even the oldest constant, the sun, is writing a new stanza in its poem, and you're reading it as it's being written. That's rare, that's special, and if nothing else, it's a beautiful reminder that certainty is an illusion. Even the giant burning ball in the sky is winging it more than we thought. So if you wake up tomorrow to a sudden surge in aurora alerts, or a news flash about a surprise flare that scrambled radio signals in the Pacific, just nod. You knew. You were paying attention. And the sun? It's getting a little weird. But then again, aren't we all? When the grid goes ghost, the lights go out. Not in your house, not in your neighborhood, but everywhere. Street lights vanish. Phones die mid-scroll. The hum of air conditioning, the invisible flow of digital life, the comfort of modernity, silent, gone. Like someone snapped their fingers and the 21st century disappeared. This is what happens when the grid goes ghost. Not from war, not from sabotage, but from the sun. Let's walk it out slowly, like a dream. It starts with a solar flare, massive, fast, aimed straight at Earth. Within minutes, X-rays and extreme ultraviolet light hit the upper atmosphere, ionizing the ionosphere, disrupting radio signals, and bending GPS accuracy into useless spaghetti. Then a day or two later, yes comes the real punch, the coronal mass ejection, a blob of solar plasma, trillions of tons of magnetized solar material hurtling toward Earth like a cosmic wrecking ball. And when it hits, the magnetosphere buckles, charged particles pour in, Earth's magnetic field ripples, twists, and reconfigures. Long power lines, especially across North America and parts of Northern Europe, start to hum with extra current. Transformers begin to overheat. Control centers see warning lights flash. And then, one by one, they go dark. First Quebec, then Maine, then New York. The eastern seaboard tips over like a row of dominoes, not because someone pulled a plug, but because invisible hands pushed a magnetic field out of balance. Historians still argue whether we're prepared. Some power companies have installed special blocking devices, GIC blockers, to stop geomagnetically induced currents from flooding the grid. Others haven't. The U.S. grid, famously patchwork, is a combination of hardened infrastructure and ancient transformers older than some of your coworkers. And those transformers, they're fragile, heavy, expensive, built to order. If they melt, replacements take months to manufacture. And that's if the factories have power, which they probably won't. This is why space weather experts talk about grid vulnerability with the same haunted look meteorologists get when hurricane models go spaghetti noodle across the Gulf of Mexico. The models aren't great, the timing is fuzzy, but the risk is very real, and not just for electricity. Water treatment plants depend on power, so do natural gas pumps. So gas stations, cell towers, hospitals, airports, all of it woven into a tight web of assumed continuity. Pull one thread, and the whole thing unravels. Fringe scenario time. Imagine a solar superstorm like Carrington or 774 AD hitting today. Not a mild storm, not a few satellites glitching, but a full-on space hurricane. Models suggest that in such a case, up to 40 million people in the U.S. could lose power. Long-term, weeks to months. In summer, no AC. In winter, no heat. Cities would get weird fast. No ATMs, no online banking, no traffic lights, no logistics networks to restock stores. Refrigerators warm, medication spoils, communications go fuzzy. It wouldn't feel like an apocalypse. It would feel like a slow unraveling, like the world forgetting how to function. And while you're listening to this in the comfort of light and signal, sort of you should know, the only reason it hasn't happened yet is luck. NASA's Stereo A satellite caught a Carrington-class CME in July 2012 that missed Earth by 9 days. If the flare had erupted just a little earlier, we would have been in the crosshairs. Instead, it sailed past us, hit nothing, and fizzled into the cosmic sea. A close call, one we only understood after the fact. Now satellites like SOHO and Discover sit out in space like nervous lifeguards, watching the sun's surface for early signs of trouble. If a CME is spotted, alerts are sent. Agencies like NOAA's Space Weather Prediction Center and NASA's Solar Dynamics Observatory start pushing updates. Power grid operators brace. Airlines reroute. But if it's big enough, there's only so much bracing you can do. A few governments have emergency protocols in place. FEMA has a solar storm plan, so does the European Space Agency. Some emergency kits now include space weather checklists, which feels both incredibly cool and deeply unsettling. As if we're slowly admitting the sky might get cranky one day. You might think, well, I have a generator. Sure, but how long can it run? And what happens when the fuel runs out or the GPS network guiding your fuel delivery can't find your address anymore? No internet, no supply chain, no location services, no cloud backup. The cloud would literally vanish. And yet, in the quiet, some things would return. The stars would shine brighter without city light. You'd see the Milky Way again, an actual band of light across the sky, not a smudge from a forgotten childhood camping trip. You'd hear birds more clearly, the wind through the trees, maybe even your own breath for once. People would talk, share firewood, trade batteries, rediscover paper maps, cook meals with neighbors, and slowly maybe, just maybe, rebuild. Not back to what was, but forward to something more aware, something less fragile. Fringe idea from the anthropologists. The collapse of some ancient civilizations may have been hastened by solar storms. Crop failures following climate shifts, navigation errors, the loss of timekeeping accuracy, all of it tangled in a chain of dependency. History doesn't repeat, but it rhymes. And you're safe. The grid is still humming. The sun, for now, is merely glowing, not growling. But if the lights ever do flicker out and stay out, remember this: the world didn't end. It paused. And when the grid goes ghost, the sky comes alive. You'll look up, and maybe, just maybe, the auroras will dance across your neighborhood. No phones, no tweets, no filters, just sky fire. The kind that reminds you you're on a planet, under a star, wrapped in light, watching the sun while you sleep. The world doesn't stop when you do. While your body finally lets go and begins its gentle drift toward dreaming, somewhere, maybe in Boulder, Colorado, maybe in Tokyo, maybe in a garage observatory behind someone's house, in a suburb you've never heard of, someone is watching the sun. Actually, not someone, thousands of someones. Some wear lab coats, some wear hoodies, some haven't worn pants in days, but all of them are tuned in to the same glowing giant in the sky, watching every twitch of plasma, every magnetic ripple, every new sunspot twisting into view on the solar limb. Because the sun never really sleeps, and so, neither do its observers. Let's start with the professionals. NASA, ESA, JAXA, NOAA. These agencies operate an intricate ballet of spacecraft and ground stations, each pointed toward the sun like nervous deer staring into headlights that just happen to be 865,000 miles wide. Satellites like the Solar and Heliospheric Observatory, SOHO, Parker Solar Probe, and Solar Orbiter beam back constant streams of data, images, particle counts, magnetic maps, plasma velocity graphs. It's not glamorous, it's not loud. Most of the time it's just silence and pixels. But when something starts to change, when a flare blooms or a sunspot twists like it's winding up for a pitch, suddenly everyone leans in. You picture them, space weather analysts at NOAA's Space Weather Prediction Center, sipping cold coffee and watching red lines twitch up on a magnetometer graph. Someone mutters KP7, and a tech quietly sends an alert to power grid operators across North America. That's the professional side. But the sun doesn't belong to the professionals alone. Out there in the quiet dark, amateur astronomers keep vigil too. Some are retirees with solar telescopes mounted on backyard rigs. Others are teenage YouTubers tracking sunspot counts from secondhand observatories. There's even a whole community of ham radio operators who monitor solar weather not just for fun, but because their radios sound different when the sun gets feisty. Fringe fact for the curious: some hams can tell the level of solar activity just by the tone of their transmissions. High solar activity improves long-range communication on certain frequencies. And to them, a flare isn't a threat. It's a chance to talk to someone in Antarctica using a wire and a will. Every night, while you sleep, someone posts new solar images to forums. Another uploads time-lapse videos of sunspot rotation. Someone in Finland checks the aurora forecast before heading out with a camera and a thermos full of something hot enough to thaw a mammoth. This global constellation of watchers, some paid, some passionate, forms the first line of defense against solar chaos. They're not just gazing, they're measuring, interpreting, warning. The sun has become, in a way, Earth's most monitored threat. Historians still argue whether this level of attention is new or just better equipped. Ancient sky watchers built entire temples to follow the sun's path. Stonehenge aligns with solstices. When the Maya tracks solar eclipses with the precision of NASA flight software, just with fewer acronyms. But today, we don't just watch the sun. We predict it. Sort of. Despite all the satellites and supercomputers, forecasting solar activity is still closer to weather than clockwork. You can tell when the conditions are right for a storm, but whether it happens or how strong it'll be is a coin toss in space plasma. That's why the watchers don't sleep on the job. Right now, literally as you lie there, a new sunspot group may be rotating into view. Scientists are analyzing its magnetic complexity, ranking it by the Mount Wilson classification system. Yes, sunspots get grades too. If it's an alpha, no big deal. If it's a delta, buckle up. They'll check for magnetic shear, for complexity, for signs of tension. Or like meteorologists reading pressure fronts before a hurricane, and they'll post, update, alert, not in panic, but in routine. Because this is the world we live in now, a world with an always-on star and an always-watching species trying to stay one solar sneeze ahead of disaster. Somewhere right now, a school kid is refreshing a solar flare tracker on their phone. A radio geek is checking the A-index. A satellite operator is glancing at the space weather dashboard and silently hoping today isn't the day. And here's the quiet beauty of it all. You don't have to do anything. You don't have to monitor the sun, or decode magnetograms, or read solar flux reports, because someone out there already is. Dozens of them. Hundreds. Watching while you rest. And if the sun does flare big, if a CME launches and sets its sights on Earth, they'll know. They'll tell the agencies. The alerts will go out. Flight paths will shift, transformers will brace, the internet might hiccup, but it won't vanish. Not if the watchers get there first. It's a kind of invisible safety net, one stitched together with code, passion, and caffeine. A global neighborhood watch for a star that doesn't always knock before it kicks down the door. So go ahead, sleep. The sun is still glowing, still throwing tantrums, still boiling with the kind of power that could turn satellites into paperweights. But you've got eyes on it. Every continent, every time zone, every night. And while America sleeps, someone in Australia just clicked record on a sunspot video. Someone in Norway just finished uploading aurora photos. Someone in India is calibrating their solar filter, waiting for sunrise. The watchers never left. Not a 1 star, 2 billion questions. The sun is still there when you wake up, has been for about 4.6 billion years. A little wrinklier, a little wiser, still dragging Earth in circles like a cosmic chaperone with a nuclear engine. You stretch, blink, and squint into that familiar golden light pouring through your window, and you feel safe, comforted, seen. But now you know too much. You know that while you slept, it pulsed, flared, maybe even ejected a plasma cloud the size of a planet into space. Maybe not toward Earth, this time. But somewhere, some unlucky speck of rock is about to have a very bad day. Because the sun, for all its charm, doesn't play favorites. It's not angry. It's not kind. It's just active, always. A ball of roiling plasma, tangled in its own magnetic nerves, throwing light and radiation into the void and calling it balance. And despite all we've learned, there's still so much we don't know. Take sunspots. We can count them, name them, watch them rotate and flare. But why do they form in such complex magnetic knots? Why do some unleash fury and others just fade away? We have models, equations, but every time we think we've got it pinned, the sun surprises us again, or solar cycles. Sure, we can measure the 11-year pulse, the rise and fall of activity, but sometimes it double peaks, sometimes it lingers, sometimes it slumps into a minimum that lasts for decades, like it's sulking. Is it driven by deep convection patterns, planetary alignments, internal mood swings? Scientists argue. Papers are published, new satellites launched. Still, questions. And then there's the big one. And will there be another Carrington event? Probably. Will we know it's coming? Maybe. Will we be ready? That one's tricky, because the thing is, we live in a house of glass, and the sun throws stones. Most of the time, it's polite about it. A few flares here, a minor geomagnetic storm there, a satellite needs a reboot, a flight gets rerouted, nothing major. But all it takes is one bad toss. And yet, somehow life goes on. You wake, you eat, you scroll, you send texts across continents at the speed of light. Light made possible by the very star that could one day cut the signal entirely. It's a cosmic catch-22. We owe everything to the sun, our warmth, our food, our seasons, our oxygen. And yet that same giver of life could strip away our technology in an afternoon if it decided to breathe just a little too hard. Fringe hypothesis. Some scientists believe the sun may play a role in shaping not just life, but consciousness. There's ongoing research, out on the edge to be fair, exploring correlations between solar activity and human mood, creativity, even bursts of innovation. True, maybe not, but intriguing. The idea that our minds are tuned to solar rhythms? Poetic at the very least. And when you think about it, why not? You're built out of stardust. Every atom in your bones was forged in the heart of a star. Not this star, maybe, but one just like it. And now, here you are, orbiting a newer model, listening to it hum while you sleep. It makes you wonder what else we've missed. What signals are buried in solar wind we haven't yet deciphered? What secrets are locked in gamma flashes and ultraviolet whispers? Are we just one algorithm away from decoding a new language in sunspots? Maybe, maybe not. But that's the fun of it, isn't it? The sun isn't just a star, it's a mystery engine, a cosmic metronome, a temperamental magnetic artist painting in auroras and radiation. And we little planetary hitchhikers get front row seats to the performance. Right now, there are scientists plotting new missions, better telescopes, deeper probes, more sensitive detectors. Some want to fly closer than ever before. Some want to study how solar weather affects exoplanets. Some just want to watch and listen and try to understand. Because the sun, for all its light, still keeps a lot in the dark. And you? You're one of the few who care enough to look up and ask the hard questions. Maybe not with a telescope, maybe not with math, but with wonder. And that matters. You've joined a lineage of watchers stretching back through time. Monks, mathematicians, sailors, scientists, stargazers, and insomniacs, each trying to understand that glowing orb that refuses to be ignored. So as the day begins, and the solar wind keeps flowing, and the flares keep flaring, remember this. You don't need to solve it all. You just need to notice, because sometimes the act of noticing is enough. To stand under the sky, feel its pulse, and whisper back, I see you. And with that, our journey through Earth's solar tightrope comes to a close. But don't drift off just yet. Wind down, final 300 words. Let's slow everything now. Let the storm above fade into the distance, like a thunderhead retreating across a forgotten sky. The auroras quiet, the particles settle, the flares curl back into the sun's surface, And the magnetic field around you exhales, soft and silent. Earth is still spinning. Satellites are still watching. And you're safe, wrapped in atmosphere and gravity, tucked beneath the gentle hum of protection. You've heard the warnings, the mysteries, the flare-ups and flips, but you've also seen the beauty, the glowing rivers of light, the ancient tree rings whispering secrets, the shared watchfulness of people across the planet. It's not fear that remains, it's reverence. The sun will rise tomorrow as it has always done. You don't need to understand every gamma burst or sunspot. You just need to rest, to trust, to remember that even in uncertainty, there is rhythm. In chaos, there is awe. So breathe deeper. Let the soft weight of knowledge become a blanket rather than a burden. You've listened well. Now let go. The night is still. The sky is patient. And the sun, it will wait. Good night, space traveler. Sleep easy under the ever-burning light.